before we get going with anything on the screen, I'm going to stand up and give you a demonstration. Okay. All you have to do, now this is not a trick question, all you have to do is count how many steps you hear me take. Why did I say hear? Because you're all going to close your eyes. All right? And a bunch of you won't close your eyes because you're like, oh, I'm too cool to do that. But I'm going to request that you all close your eyes and listen. And all you have to do is count how many steps you hear. Everybody ready? Eyes open. How many steps did I take? Okay. It was 4. It doesn't matter. Don't worry about it. That's not what's important. Where am I standing? In the exact same spot I started in. So, if I had moved like a ninja, of which I am capable due to the fact that I do have a black belt in karate, if I had moved like a ninja and your eyes had really been closed, would you know if I moved or not? You would not. Why? Because I'm back where I started, right? That is displacement. You know I moved 4 steps because I stomped, yes? And yet here I am back at the same spot. Now, how far did I actually travel? You do know because I took 4 steps. You heard me. I moved 4 steps. But I displaced myself not at all. Do you all understand? Now, if I move those same 4 steps as a distance, because distance has no direction, I will not end up back here, will I? 1, 2, 3, 4. And I'm way over here, yes? So I've gone the same distance as I did when you had your eyes closed, and yet I am way over here. So I have been displaced by 4 steps, and I have gone through 4 steps of distance. Everybody good? But when I was back here, and your eyes were closed, I went through 4 steps of distance. 1, 2, 3, 4, but my displacement was the same. Everybody cool? Okay, now, listen carefully. This is where it gets weird. In real life, how many directions are there? Don't say 4. Infinite. Excellent. There's an infinite amount of directions, yes? Because I could go in any direction in a 3-dimensional circle from where I am, yes? Okay, good. In math, with numbers, how many directions can I show? In math, with numbers, how many directions can I show? 2. What 2? No. Negative and positive. When we are using numbers, we only have 2 possible directions. And yet, we must use numbers to represent data, yes? So, here is what math dudes and physics dudes and dudettes have decided. Positive numbers represent a few different things. They represent north. They represent forward. They represent to the right. They represent east. And most importantly, they also represent up. Most importantly, they represent away from your starting position. So, when I stood up and I took 2 steps away, I went through 2 steps of distance, yes? 2 steps. Everyone agree? What was my displacement? No, right now, what is my displacement? No, 2 is my distance. Displacement must have a direction with it. I went away from my starting point. So what was it? Positive 2. I went to my right, so you could say positive 2, yes? I also happen to be going north, which is positive 2. Now, where it gets weird in this example is I've moved to your people's left. So you might say negative 2. Everybody cool? So that's why I like to use the away from and back to start. So right now I'm at positive 2 displacement, yes? Now if I go back to start, that is negative 2 displacement, yes? So my displacement is 2 plus negative 2, which is 0, which is why I'm back where I started. What was my distance? 4, because there's no direction in distance. 1, 2, 1, 2. Everybody good? Now you are intelligent young people. If all of those are positive, then what are the negatives? The opposites. South, back, left, west, down, and back to start. So, if you drew the yellow line, which most of you did, you drew a good displacement graph. If you drew the blue line, you drew a distance graph. Now, please notice the only difference is they are mirror images of each other, yes? If I drew a line, a dotted line right here, and I picked up my tablet and I folded it in half, then this line would be exactly on top of this line. Does everybody understand? Yeah? Okay. All right, so let us move on then, cabbages, to a second kind of graph. Now look closely at this graph and tell me how it differs from the distance and displacement graphs we just did. Jacqueline, go. It has to do with speed. Now on a distance time graph, we know how to do speed, don't we? We found the rate of change, yes? We knew on a distance graph that we could check this, right? So we went 140K in 2 hours, which we changed to 70 kilometers per 1 hour, yes? But on this graph, I've already got speed. It's there. But you can see I still have a change here, don't I? What do we call it when we change our speed? It's acceleration, right? So on this one, we can still use this move to tell us the rate of change. But now it will be the rate of change of speed, which is just acceleration, yes? So at the beginning, she is not moving at all. So her speed is obviously 0. Here, her speed is 8 meters per second, yes? And this is how long? 2. So she had 8 over 2. So her speed went to 8 meters per second in 2 seconds. Now we're smart kids. Do we do acceleration that way? We do nothing that way. Why would we have it over 2? What is it really? 4 meters per second per second. Yeah? Everybody cool? Okay. Now, of course, this actually is 4 divided by seconds, isn't it? Right? So in physics, we write 4 meters per second squared, because that is the denominator as well. Right? Everybody cool? So that's how fast she's accelerating. Now, let's talk about what is happening on this graph. What is happening for the first 2 seconds? Jacqueline. So from O to A, She starts and speeds up to what? No, that's how fast she is speeding up. She speeds up to 8 meters per second from 0. Everybody cool? 8 meters per second. What happens from A to B? She stays, what do you mean she stays there, Pradeep? She stays at 8 meters per second. Does she stop? No, because this is not a distance time graph. On a distance graph, if there's a flat line, that means what? They've stopped. They're not moving. But on this graph, because it means speed, she maintains. She stays at 8 meters per second, which is pretty darn fast. Right? Now, what happens from B to C? She slows down, right? We don't like to use the word decelerate, especially physicists. They will say negative acceleration because they're kind of different, but I'm not getting into why they're different. If you guys want to say decelerate, that's fine. B to C, she slows down. Why? The race is over. When is the race actually over? When does she cross the finish line? At 14 seconds, doesn't she? Because why would you slow down before the end? Alicia's an athlete. It's a 13-second race. You don't think she can maintain full speed for 13 seconds? 14 seconds. Whatever. Okay. Addison?
Well, how do we know when Alicia's race ends? How do we not know so that it ends at 16 seconds?
Well, again, why would she slow down before the finish line?
Because she doesn't know how to keep her pace and she can only go...
Okay, Addison, you want to play lawyer ball? You write that down. Obviously, the best answer is what? I'm asking. Why do you think I am saying the race ends there?
Because she should keep full speed. And then
Right. Now let me ask you this: if it is a 16-second race, and she runs as fast as she can and then slows down to a dead stop right when the race ends, have you ever seen a race run that way? So stop playing lawyer ball. Okay? Watch the Olympics. Do they run up to the tape, stop, and then just go like this? No. Have you played baseball?
No.
You've never played baseball in your life? Okay, let's try soccer. You run up to a penalty kick to kick the ball to score. There is the ball. Do you run up like this? Full speed, stop. No, what do? You run through the ball. So, stop playing lawyer ball, all of you. Aight? Huh? What? I didn't say you did, but at some point in the year, every single one of you will play lawyer ball. I'm warning you to stop. Okay? Okay. Back to where I was talking. Some kid always says, well, if the race ends at 14, why isn't that a straight line? She cannot stop, so she is not running into a wall, although that would be wicked Olympics. The finish line is a brick wall, and you actually have to hit it at the fastest one so you can't slow down. It would kill them. But the way what interests you people based on, popular fiction and movies, you would probably watch Olympics like that. You would not watch... If javelin was instead javelin catching, you would probably be all watching it all day. You don't want to watch anybody throw a javelin, but you'd love to watch people catch one. Right? I know. I mean, the books you read, the movies you watch are all about killing. So, when I was your age, a guy in Newfoundland was walking across a field, an official in a track field took a javelin right here. They showed the X-ray in the magazine. It's like, and it goes in just under his jaw, and it sticks out right here. The guy was fine.
There's a dude that got a
Yeah, that's Phineas Gage from way back in the day blew up a rebar thing and it went through here and severed his brain. But he was fine. Well, not fine. He turned into a raging a-hole. He was a super nice guy, but it severed the corpus callosum, which is the thing that attaches your left and right brains, and it completely changed his personality, but he lived. All right. We appear to be good. So let's turn the page over, and on page 88, you people are going to draw 4 graphs for me. Now listen. Listen. Draw them in pencil on the left. So if you've screwed them up, you can fix it on the right. Okay? Go. Okay. Height versus time. First of all, what's going on the independent axis? No.
No, wait. Independent is by itself, not
Time. This is height. Now, here's where it starts to get technical. Can you put your first dot right at that corner? No. Because the swing does not sit on the ground. It would be very hard for it to swing if it was sitting on the ground. So the swing is a little bit off the ground. So if you have your dot right in the corner, fix it. Next, as you back up to swing, what happens to the height of the swing? It goes very slightly up, right? Then what happens when you lift your feet? It goes down. Does it ever go below this dotted line? No, because that's the bottom of the swing. What happens as you get to the bottom of your swing? You go back up. Do you go slightly higher? If you know what you are doing, yes. Or if you are a lazy sack of crap and dad is still pushing you when you're 12 years old, you will still go slightly higher. What will happen then? You will go back down. Will you ever go below that? Now, does speed start to increase as well? So what happens to each of these curves? Does it get steeper or shallower? Steeper. Will it ever go straight vertically? Why not? Time does not stop. Time is on the bottom. A straight up and down line means time has stopped. Right? Will you ever go all the way around the bar? No, you haven't. No, you haven't. Because you cannot. It is impossible on a swing with chains to go all the way around the bar. Okay, Pardeep, bring me video. Because you can't do it. You cannot go all the way around the bar. Listen to me. You cannot go all the way around the bar powered by humanity on chains. You must have solid bars. You're welcome to prove me wrong. I will gladly get a field trip and go to a swing set so you can prove it. No. I will get permission slips and everything because I know I'll win. You cannot do it. They couldn't even do it on Mythbusters with rockets. You can only do it if the swings are on bars. Because once you get up this high, you cannot generate enough speed to get all the way around and not fall straight to earth. Because this chains won't hold you up. He's welcome to prove me wrong. I would kill to see it. It can't be done. I know. But it won't matter. Now, some kid every year draws the swing like this. And I was like, wow, kid, you swing really fast. What do you mean? Well, you're going back in time. You are swinging faster than the speed of light. Oh my God, kid, you haven't even sat in the swing yet. You're already back here. Because graphs are not what? They are not, pardon me, Ron? They are not representative of real life. They represent the data of real life. Gersahill.
So, as a serious question,
Oh, okay. That's a refreshing change.
would you be able to put the arrow on the graph
What do you mean an arrow?
to show that it keeps going on?
Well, I mean, yeah, technically, right? You could do that if it was going to keep going forever. Now, what will happen on this graph? Eventually, you get to a maximum height, right?
Yeah.
And a maximum speed, and that could carry on until you get tired or barf, depending on how old you are. Because old people have a lot of trouble on swings. My wife can't go on swings anymore. Like 5 or 6 swings, and she feels sick. I can handle a swing for a while. But I am now to the point where I can't ride certain rides at amusement parks. I can't do any backwards roller coasters. They make me barf every time. I can't really go backwards on a ride anymore. But that's because humans, as you get older, you guys may not know this, but your sense of balance is liquid in your ears. Your ears have this thing called the semicircular canals, and it looks like a mutant Mickey Mouse. And your balance is set by fluid that flows through these canals. As you get older, the fluid gets thicker and can't flow as well. So you can't keep your equilibrium, which is why old people can't do rides anymore. So when your dad and mom say, oh, I just can't go on it with you, don't give them a hard time. They are physically unable to do so. What?
Can that thing like just not work at all?
Yes.
That mean you just can't stand up? Or you
Yeah,
can't sit down?
that's vertigo and stuff like that. It's often related to defects in your semicircular canals.
Does that mean you have to lay down at all times?
A lot of people, well, not a lot of people, but there are people that have that, like people but it also has to do with blood pressure and other things, right? If you can't get enough blood in your brain. My wife has really low blood pressure. If she stands up too fast, she gets dizzy. All right. So, now, graph number 2. Distance time for a runner completing a 400-meter race. My pen has died. I'm hoping I'll be able to make it work for this. What's down here? Time. Why? And what's over here? Distance. This is such a piece of crap. Didn't do it once yesterday. Distance, right? Okay. Your first dot is going to be where? Is it going to be right in the corner? Yes, because in this one you have traveled no distance at the beginning of the race. What number would go up here? 400, because it's only a 400-meter race. It's a distance time graph. So, all right. So, I'm going to do this now because this is such a piece of garbage. I'm going to do this now. So this is going to be, fine, we'll say 500. 4, 3, 2, 1. You will need a dot somewhere out here. We'll say it's 90 seconds, because that's a decent 400-meter speed. So at 90, you'll have a dot around 400, yes? Right? Now, how you connect those dots does not matter, as long as they're connected. What are the things that aren't allowed to happen? Time can't stop. So can there ever be a straight vertical line? No. What else can time not do? Time cannot go backwards. So will you ever have a line going that way? That way. No. So as long as you have a line between this dot and this dot, you have done it right. Now, if that was the line, is that a realistic representation of a race? No, why?
You don't travel as much.
You don't-
You don't travel as much at the beginning as like the rest of the race. You don't travel as much at the end as the rest of the race. Because you have like the time where you're going.
Speeding.
Yes, thank you. That's what I'm looking for. You change speed, yes? You do not run at a constant pace. So, usually, how would a race start?
Slow.
You start out at a good little pace to get in a good position, yeah? So you might start out pretty fast. Then what would you do? Slow down to a decent pace, yes? So then you might level out a little, and then what do you do at the very end? A little sprint. So that is a better real life graph, right? But as long as you have connected the two, you've done it correctly, all right? And there's no vertical lines and none of this. Oh, I'm slowing down, right? Can't go backwards. Everybody cool? Yeah? Okay. Now, how is number 7 different? What's different about number 7, which is a displacement time graph? What's different about displacement time? And it's on a track. I know one of you can figure this out while I erase the rest. Addison.
Isn't your like graph gonna look like a hill? Because like the farther you're going away from the start point, and then the closer you get.
So, what changes? Does time change? No. Distance is now displacement. Now, if it's a track, where do I end up? As Addison says, where do I end up?
At the beginning.
At the beginning.
After the line.
Right? So if I start here, I'm going to end up here at 90 seconds, yes? Okay. How do I run? I start out what?
Start out close to the start.
I start out close, and I'm probably going a little bit fast, yeah? Then what?
You get farther and farther away.
I'm getting farther and farther away, but at a slower pace, yeah? At some point, I'm halfway through the race, yes?
Yeah.
So what happens?
Start coming backwards.
I start coming back. Do I keep the same pace? Most likely. And then at the end, what do I do?
Straight.
Real steep, right?
No.
Wah. I screwed this up at the beginning. I drew it absolutely backwards. Sorry. We start speedy, then we flatten out, then we flatten out, then we finish speedy. No, I went this way. I went flat, then up. Now, everybody cool? Everybody understands?
I just drew a mountain.
Yeah, that's fine. It's fine. It's fine. The point here, the concept is that it's displacement as opposed to distance. And last, look at number 8. Do I use the word displacement or distance? What word do I use? Position. Now, what do you think the word position lends itself to? Displacement or distance, Jacqueline? Displacement, because position matters about graph, yes? Position matters about direction, doesn't it?
Yeah.
Okay, so everybody's is going to be different today for number 8, yes? Because how many of you ride the bus to school? Okay, how many of you walk? How many of you ride a bike? Anyone? How many of you ride a skateboard? How many of you ride a Segway? How many of you ride a kangaroo? Yes. How many of you get to ride with your parents? Okay, so everybody's going to be different, right? So I can only do mine. All right, now, position as you travel to school. Will your graph go back to the bottom? No, because we are only going to school. What if I told you to do all your position in a day? Then it would go where? Back to zero, because you'd end up back at home eventually, right? Okay, so for me, I drive to school, yeah? It takes me 30 minutes, and I live 32 kilometers away, so I'm going to go up to 35. Everybody cool? Okay, so I back out of my driveway. How fast am I driving?
65 kilometers an hour.
Hey, you're right. I drive like a stuntman. I look backwards, nobody's there. I floor it, spin the wheel, do a 180, boom, down the road. But seriously, how fast am I driving?
Probably like 20.
Yeah. Okay, so I'm going to start out real slow, right? I live 8 kilometers from the highway. On that way, I go through 1, 2, 3 stop signs. So, if there are 3 stop signs between me and the highway, how many flat lines am I going to need? 3. Are they going to be long? No, it's just a stop sign, right? And I'm not going very fast. So, 35, 5, 10, 15, 20, 25, 30, 35. Cool? Yo. I just told you I only go through 3 stop signs. Then I would stop for longer, because stop lights are longer than stop signs. Stop playing lawyer ball. A minute. So I am 8 kilometers from the highway. So I'm going to drive a little bit. Now my first stop sign is literally at the end of my street, right? It's not going to be anywhere close to a whole kilometer, is it? So I'm going to go a very little bit, and then I have a flat line for my stop, yes? Then my next stop sign is again not very close. But then I drive about 3 kilometers before a stop sign. Then I have my stop sign, and then that stop sign is very close to the highway, which is 8 kilometers away. So here I am at 8. What happens when I hit the highway?
Floor.
So what happens to my graph? Does it get steeper or shallower? Jaden. Why? I'm going faster. I'm taking up more distance in less time. So I'm going to go almost up to 25 pretty darn fast, right? So to 25. What happens at 25, do you think? Why? I'm exiting the highway into Abbotsford, yeah? So I got to go back to there's a stop sign, flat, stop sign, whatever, and I end up at school. Everybody good? Now, if my trip home is exactly the same, what would this look like? A mirror. What if I hit traffic on the highway? What would happen to this part?
It would become more shallow.
There's an accident, I can't move. What happens? What stops?
You. Your distance.
Not time. So what happens here?
Straight line. Straight horizontal line.
Now the accident starts moving real slow. So I move a tiny bit of distance in a long time, then I stop again. Tiny bit, long time, stop again. Tiny bit, long time, stop again. Then I get back to normal speed. Everybody cool?
Yeah. Let's pause another one.
Now, you guys would be different. First of all, none of you live 35 kilometers from school, right? So,
I live 2 kilometers from school. I'm 3 minutes.
so you get a ride to school?
Yeah.
Okay, so we'll go 2 kilometers, you say?
Yeah.
So 0.5, 1, 1.5, 2. And you take your, 5 minutes you said?
3-ish.
3 minutes in a car? 1, 2, 3. So, again, he's probably going to start slow for the first minute, maybe the first 500 meters as he gets to the end of his street.
No, I live in complex, so like the first 30 seconds slow.
Okay, so maybe 250 meters?
Yeah.
Okay, then what? Then he hits the street.
Yeah, and so there's a stoplight.
So he speeds up a bit, hits a stoplight.
Yeah.
Then he speeds up a bit till he gets to the school.
No,
Then what happens at school?
that's not the school yet.
Oh, we're still not at school. Okay, keep going.
We have another stoplight.
Another stoplight.
We speed up again. Another stoplight.
Another stoplight.
We speed up again. And another stoplight, and that's where I head out.
And you get out at the stoplight.
Yeah.
Easy peasy. Everybody good?
Yeah.
If you walked, would it look like this? If you walk, is it possible to have none of these? Right, so you could jaywalk, right? You say, I got to cross the lights or I'm going to cross, right? It's possible. What would you do what would Braden's graph look like if right there, halfway in his drive to school, he says, damn, I forgot my math binder at home. It would go back down to the here and start again. Would it ever do this? Why? You can't go backwards in time. Never. Never. Never.
What if there is a way to go back?
First of all, time is not real. Time is an invention.
Yeah, that's why we can go back.
No. No. Well, in the sheer physical reason, Braden, the Earth is moving through space at something like 70,000 kilometers an hour, yes? So if you went back in time, Earth would not be where it is right now. Because every second we move 70,000 kilometers. So if I tried to go back in time right now, 1 second, I would end up in the middle of space. Because Earth is gone from here. Because we know Earth is moving through space. Now, technically, we could have a philosophical argument that says we are all nothing but brains in a jar in some lab. I'm agreeing with you. You aren't winning this lawyer ball argument. I am agreeing with you. We could very well be brains in a jar because we are nothing except stimulation of our brains, which means, technically speaking, we could be a brain in a jar with a bunch of wires stuck to it, just like in the Matrix. That is entirely possible. It is entirely possible we do not exist. It is entirely possible we are some other culture's Fortnite. That we are living in a simulation. What?
Have you seen that movie, like Jim Carrey, and his life turns out to be a movie that has
Yes, The Truman Show. Great film. All right, listen please. Your homework is page 89. Now look please. Look please. 89 to 91 looks like a crap ton of work. But it's really not. It's because there's so many pictures in it because of graphing, right? If you need to make a graph, if you are the type of person who cannot possibly imagine sketching it like I've been doing it, get some graph paper. But it is perfectly legitimate to sketch it. Okay? Remember, when you decide to slack off, and notice I did not say if you decide to slack off, when you decide to slack off, make sure that you can do at least the questions in section C, 16, 17, and 18. Because when you decide to slack off, if you cannot do them, then you do not know what you are doing, which means you should not have slacked off. Clear? Excellent. We will move our cumulative exam to October 29th, which is next Tuesday. And I will continue to do questions on the board to keep the old stuff fresh in your mind. I apologize that that has happened, but I feel it unfair to you to do the cumulative before we have gone over your polynomial test. And I feel it unfair to give you the cumulative on a short day, which is why it was going to be on Tuesday, because we had 2 short days last week. Right? What should have happened was we should have been going over your polynomial test Monday, but then I was sick Friday, right? So I couldn't mark it Friday. It's just a bit of bad luck.